today, speaker is guest only, and he will again speak on the KAIST groups in real projective geometry. Okay, so go ahead.
Okay. Thank you very much for everyone. Okay, so today, I try to continue this lecture about the KAIST group in the real projective geometries. So let's try to remember what we learned the last lectures. So we learned last lectures first what is a KAIST group, and then also we learned the nerve of the KAIST group, and then particularly we play with the one particular examples. So this one, right? So these examples, and then we realize that the nerve of this KAIST group WS is the three-dimensional sphere, right? And then because of that, we also know that the boundary of this KAIST group also the three-dimensional sphere, and also we can easily check that this KAIST group is word hyperbolic, right? So those kind of the properties we learned the last time. Okay. So today, so we wanted to actually construct some interesting examples using those KAIST group, particularly, for example, this KAIST group WS. And what kind of the interesting example I want to construct. So the second lecture's title will be the Cauchy-Fuchsian group. Okay, so to talk about, so let's begin with what is the Cauchy-Fuchsian group. So the gamma here is a finitely generated group, and the representation law, so from the gamma into the isometry group of HD plus 1. Okay, so of course the HD plus 1 is a D plus 1 dimensional hyperbolic space. This representations or the homomorphism is Cauchy-Fuchsians. So this is the definitions. If it is discrete, so it is discrete, means the image is discrete and the faithfuls, so injective, and then this image is convex co-compact. And its limit set is homomorphic to the D-1 dimensional spheres. Okay, so this is a definition of the Cauchy-Fuchsian group. Then probably I think you already learned what is the convex co-compact means, right? So, but I try to remind you. So in this case, of course, you already also learned the more general concept, which is anisotropy representation, I guess. But before this general case, this convex co-compactness is really the motivations. So, but anyhow, I try to give the definitions for in this setting. So what is the convex co-compact? This image acts the properly discontinuously. So properly the discontinuously and the co-compactly on some non-empty convex and closed subset of the hyperbolic space. So D plus 1 dimensional hyperbolic space. So that's the definition of the convex co-compactness in this hyperbolic space. Okay. So let's give the examples for this Cauchy-Fuchsian group. So examples. So the first example is Okay, as you already guessed, so the function representations. The function representation. So what is function representations? So I will take gamma is a uniform lattice. So uniform lattice of isometric group of hyperbolic D space. So what it means? It means simply that this gamma act hyperbolic space co-compactly. Okay, so that's this discrete group which is acting co-compactly. We usually call the uniform lattice of isometric group of hyperbolic space. Okay, so if I take this one and then I can insert into the bigger one, which is of course isometric group of hyperbolic D+1 space, right? And then I take the decompositions. So this is, I will write the row 0, and this one is quasi-function representations. So probably I think I try to draw the pictures. Okay. So here I have a hyperbolic 3 space, for examples. And in the middle, so here, so this is my H2. Okay. So if you think of the uniform lattice of isometric group H2, then of course, the limit set is exactly this the black circles, right? So that's homomorphic to S1, right? And then this is this group act properly discontinuously co-compactly on the H2, right? That is the convex, of course, in H3 and also the closed. So these function representations is, of course, the quasi functions. Okay, so this is a typical examples, but then we can take the small perturbations. So any small deformations. So let's say the rho T, which is gamma into the isometric group of H D+1, of course, of rho 0 is quasi-functions. Okay, so of course, if you look at the limit set, it looks quite different. So maybe if I draw some different limit set, but still homomorphic to the S1. So in the previous example, so, but, and then also you can see that this is the convex co-compact. So any small deformations of function representations is quasi-functions. Okay, so these are the examples. But the main questions I want to ask is the following questions. So assumes we have representations. Assume that the rho, my representations, HD+1 is quasi-functions. Then is gamma is always the isomorphic to a uniform lattice. Of isometric group of HD. Okay, so previously the example produced by this way using a uniform lattice, and then we deform it, but that's everything. So that's the questions. So of course, this answer is yes, then probably I cannot continue the second lectures, but the answer is no. So particularly in this lecture, I want to provide this example using a Cox group we learned the first lectures. So this examples is with Ludovic Marquis, the 2019. So we can construct particularly dimension 4 and 6 using the Cox group. Okay. So before going to constructions, at least I want to mention the following remark. So here probably you wonder why I start with 4. Okay. So the remark is a Canon's conjectures. So Canon's conjectures, what is that? So if the gamma is a word hyperbolic group whose boundary homomorphic to S2, then my gamma is isomorphic to a uniform lattice the uniform lattice of isometry group of H3. So I think as many people believe this should be true, but of course still this is conjectures. So if the Canon's conjecture is true, then of course the counterexample for these questions should be the D starting from the 4, right? So that's the remark. And particularly for the Cox group, this conjecture known to be true. Okay. For the Cox group, the conjectures is true. Okay. So it really makes sense with the dimension from 4. Okay, not smaller than 4. Okay. So this is a remark. And then to construct these representations using a Cox group, we need to understand this Titz-Wimberg theories. Okay, so let's start with the kata matrix. So the m by m matrix A, so A, I, J, so I and J is from 1 to n, is a kata matrix if is satisfying the following conditions. The first one, all the diagonal entry should be 2, and off diagonal entries should be always less than equal to 0, and as soon as Aij is 0, then Aj should be also 0. And then another condition is that for the I different from J, if I multiply Aij and Aj, then this number is always bigger than equal to 4 or equal to 4 times cosine square pi over Mij. Of course, here the Mij is positive integers. Okay. So this is my kata matrix. Okay. And then the kata matrix is reducible. So the kata matrix A is reducible if A is the direct sum of the smaller matrix after simultaneous permutations on row and columns. So what I mean is that if I arrange properly the indices, then the A can be written something like A1 and A2 and 0, 0, right? Then the matrix is reducible. This kind of makes sense. Otherwise, we call the A is irreducible. Okay. So as you guessed, that we are focused on this irreducible Catan matrix, right? Because reducible one is exactly the direct sum of the irreducible one. If this Catan matrix is irreducible, okay, so irreducible case, then we can use the by Frobenius theorems. So if A is an irreducible Catan matrix, then by Frobenius theorems, A has a real eigenvalues and or let's say the real eigenvalues. Okay, real eigenvalues. And if the lambda is the smallest, the real eigenvalues, then there exists the corresponding positive eigenvectors. The positive means that every entry is positive, okay? Then we have 3 different cases. So we usually denote by P when the lambda is positive. So this lambda is positive, then we call this Catan matrix A is of positive type. And similarly, the 0 type, when the lambda is 0, and negative type, and the lambda is less than 0. Okay. So in fact, you will actually see, I will not really mention, I will not really give details, but in fact, this positive type Catan matrix somewhat relate to the spherical Cox group. And this 0 type Catan matrix somewhat relate to the affine Cox group. And these are the remaining part, so the negative type, okay? But not exactly, but very closely related to those concepts we already learned before. Okay.
Excuse me, may I ask a question?
Okay.
So here I see that you're using Frobenius theorem to assert these properties about the eigenvalue of A. But if I remember correctly, the Frobenius theorem applies to matrices that have non-negative entries at best, right?
Okay.
So you have to do something to A, right?
Okay. Thank you. Okay. Very good question. Actually, you're right. So as you can see, but I like your question a lot. So here, the matrix A, this Catan matrix, what it looks like. So here, if I write, it might be the 2 everywhere, and not everywhere, it's on the diagonals. And then off diagonal is is less than or equal to 0, right? So I can write this one is 2 times identity plus something, but this something is actually satisfying this assumption for the Frobenius theorem, right? Does it make sense? Because okay, so might be if I take the minus, then what happens? So
okay, sure.
Yeah. So all the entry is less than or equal to 0, right?
Mm-hmm.
Okay, and then I apply the Frobenius theorems. Then because this is identity matrix, so we can do that, right? So what I'm saying is that okay, so there is something here, some positive eigenvector v, lambda v, right? But then originally this matrix A, V, okay, so maybe I should write here. So the A, V is equal to the 2 times 2 plus lambda and V. Yeah. So that's why we have these 3 different cases. Because originally this lambda is positive, right? Sorry. This is a real, right?
Yes.
And this V is positive eigenvectors. And then I said that okay, so maybe I should write that this is not the lambda because it might be confusing you. So maybe let's say mu. Okay. And then of course the lambda is this number, right? 2 plus mu. Yeah. So does it make sense, or you need some more explanation? Okay.
No, that makes sense.
Okay, thank you. But I think it's good questions. Okay, thank you. I like the question. Yeah, please feel free to ask me because yeah, I think it's better. Okay, so this is a type of the irreducible kata matrix, and then the kata matrix. A, so A S T, S T is S, is comparable. So now I want to relate kata matrix with the Cox group. So the comparable with the Cox group W S M. So you remember, so notation. So this S is a generating set. This M is this Cox matrix, right? This if for every S different from T, every pair is a different S and T, then A S T A T S is equal to the 4 times cosine square pi over M S T if M S T is a finite, and this is bigger than or equal to 4 otherwise. Right? Probably I think you guess that this should be is a reasonable definition, right? The kata matrix someone relate to the Cox group and the comparable with the Cox group if satisfying these relations. Okay, so now we have this nice kata matrix, and we want to give a nice reflection group. So to do that, I define first the free Cox group. Free Cox polytope, sorry. So the pre-Cox polytope is a pair of the projective polytope so the polytope P of SV. So here, this SV is a projective sphere. So simply the set of all rays in the vector space V. Okay. So the pair of the projective polytope P. So more precisely, this polytope P we can write. So the P is the intersections of the half space. So what is a half space in the projective spheres? So simply we take this is a linear functional alpha S. Then I think about all the vector which is evaluates in this linear functionals. Then this is less than equal to 0, and then we take the projections. Okay, so then this will be the intersections will be my polytope, projective polytope. Okay, and then we need to assign reflections. So the projective reflections. So the sigma S is simply the identity minus alpha S tensor BS. So S in S with the alpha S BS is equal to 2. So more concretely, the sigma SV is equal to the V minus alpha SV times BS. So if I take the vector which is in a corner of alpha S, then this is a fixed point set, right? Because the corner, this is vanished. And then if I take the BS, then the sigma S BS is exactly equal to the minus BS, because I assume that alpha S BS is 2. So this is a reflection vectors. Okay. So the pre-Cox polytope is simply the polytope together with the projective reflections. Okay. But then what is a nice pre-Cox polytope? That's we call the Cox polytope. So the pre-Cox polytope is a Cox polytope. So this is our main objects, right? If the gamma, the interior of P, intersection with the interior of P is always empty for all gamma, the non-trivials, where the gamma P is the group generated by these reflections. Of course, this is the subgroup in SL plus minus. So here the SL plus minus is simply the matrix group whose determinants, so each element has a determinants plus or minus 1. So that's in fact the same thing as the automorphism group of the projective spheres. Okay, so as you can see that, okay, so when the pre-Cox polytope is Cox polytope, then we have the tiling of some part of this projective spheres. That's exactly saying, right? So because this we have this interior of this P has a no intersection with the different translates when the gamma is non-trivial, right? Okay, so this is my Cox polytope, and then the really important part of the theorems of the Weinberg is the following: the pre-Cox polytope is a Cox polytope if and only if the matrix we can easily obtain from this pre-Cox polytope. So you remember the pre-Cox polytope, we have this reflections. So here the linear functional and the vector, right? So using those, we can have a matrix, right? The ST is in S, right? And this matrix is a kata matrix. And this is equivalent. So the pre-Cox superlative is a Cox superlative if and only if the kata matrix A, the matrix A is a kata matrix. So in some sense, it's very easy to check whether the pre-Cox superlative is a Coxter. Okay? So that's is really the main part of this theorem of the Wimberg. And moreover, Wimberg proved the nice property of this representation coming from the Cox superlatives. So let's P be a Cox superlatives. Of course, I should write as a pair, but sometimes it's easier just denote by P. Okay, so the Cox superlative P with the Cox group WP and this gamma P is the group generated by the sigma S, right? It's a reflection group, gamma P, right? So probably you wonder what is WP. Probably you already have a nice guess. So how we can obtain WP? So P is a Cox superlative. So the matrix A is a kata matrix, right? So you will see that kata matrix, so the previously here, okay? So Aij, Aj should be bigger than or equal to 4 or 4 times cosine square pi over Mij. So, but I didn't tell you, but this is somewhat relates to this composition of these two reflections. Okay, so the two reflections, so these two reflections will be the rotations by 2 pi over Mij when these values Aij times Aji is equal to the 4 times cosine square pi over Mij. And this composition is parabolic if this Aij, Aji is equal to 4 and hyperbolic is bigger than 4. This number is bigger than 4. Okay, so we can have this Cox group which are related to the Cox superlative P, right? Because Cox superlative P, it gives us kata matrix A, and then as soon as, for example, I and J, so sigma I and sigma J, so because the sigma I will be the one generator and sigma J will be another generator. We connect them, and then there are this label Mij. When we have this 4 times cosine square pi over Mij, which is exactly these values. Okay, so I think you can guess how we can obtain this WP. Okay, then this is important, the results. And sigma, which is representations from the WP to SL plus minus V, the every generators map to the sigma S. Okay, so this is isomorphism onto the gamma P, which is a discrete subgroup of SL plus minus V. Okay, so the discrete, and this gamma P orbit OP is a convex subset. So the convex subset I denote by the CP of SV. And then if I take the interior of this convex subset, then gamma P act properly discontinuously on it. Properly and discontinuously on the omega P, which is the interiors of CP. So it's surprisingly, previously I said that the union of, if you remember here, the Cox polytope, then this, if you consider the gamma orbit of P, then it's a tiling of some part of the projective spheres. But Wimberg showed that in fact, this is convex set, okay? And this gamma acts properly discontinuously, these interiors. Okay. So in this way, we can construct this nice convex domain, which is acted by this Cox group. Okay. So let's try to construct this representation we call the Titz-Wimberg representation from the Kata matrix. Okay, so how we can construct? So the Titz-Wimberg, the representations. So the A is my Kata matrix. So AST, ST, S, and then this Kata matrix will give us a Coxeter, sorry, the simplex. So I will denote by the delta A of RS to the RS. Okay. So the projective sphere, and then the vector space is simply the R to the S. So for the linear functioners, for T in S, alpha tilde T is simply we take the canonical dual basis of RS. Okay, so this one is a canonical's dual basis of RS. Okay, so this will be the linear functioners, and then because we have this Kata matrix, and then we can define the vectors. So take the unique vector BT tilde in RS such that alpha S tilde BT tilde is equal to the A ST for all S in S. Okay. So this is quite clear, right? But then this Cox simplex delta A is a pair of the intersection of RS and alpha S tilde X less than equal to 0, and the obvious reflections identity minus alpha S tilde tensor BS. Okay, so this is my Cox simplex. Okay, and then if I take WA is the Cox group comparables with A. Okay, so the given Kata matrix A, there is a unique Cox group which is comparables. Then, of course, as I already told you, these Wimberg theorems saying that there exists discrete and faithful representations. Sigma A tilde I denote WA to SL plus minus RS. Okay, so this is we can easily obtain from the Qatar matrix. We construct the Cox simplex. Okay, then this induce this discrete and phase representation sigma A tilde. Okay. Now I give some assumptions. So assume that A is irreducible now to make the discussion simpler and of negative type. Okay, so A is irreducible and of negative type. Then, so the previously our Cox's polytope is a simplex, the Cox's simplex. But now we can get some more general case, how we can do that. So let's be A. So this is the linear span of the B S tilde. Okay. And then this VA is preserved by the reflection group. Okay. So then, of course, we consider the restrictions. So we set alpha S is the restriction of alpha S tilde to VA. And the VS is the same vectors. Okay. But then, the previous Cox simplex, right? And then if I take the subspace, right, VA, then we have a projective polytope. Polytope PA. Now this is intersections of the half space, but this is in VA, okay? With the alpha S X is less than equal to 0. So this is projective polytope in SVA together with the reflections sigma S, so identity minus alpha S tensor VS. So this is a Cox polytope now. So might be, I think I drew at least what simple pictures. So this is, for example, previously we have 4 generators for this Cox group. So we have this, we have a Cox tetrahedrons, right? But sometimes it can happen that for this reflection vector, so it can have there are 4 reflection vectors, right, for each phase. But then this can have this produce this linear span, which is plane. So for example, you can imagine. Okay, so this is the foregone, right? So previously it was a Cox tetrahedrons, but then if in this case it can be a Cox foregons, right? So in the same way, this will induce the discrete and faithfuls the representations and sigma A, which is WA to the SL plus minus VA. And then I will denote the gamma A is a sigma A and WA. Okay. So in this sense, actually, we can produce the representation, which is irreducible representations. Okay. And then to get the representation into the isometric group of hyperbolic space, we need to assume more. Assume in additions that A is symmetric. Okay. But then in this case, there exists the gamma A invariance scalar products. So let's denote by the BA on VA, okay, such that BA BSBT is exactly the AST. Here, as I said, when we assume that A is symmetric matrix for ST in S. So in other words, that alpha S linear functional is simply the BA BS dot, okay, for S in S. So the when A is symmetric, and then there is such a gamma A invariance, the scalar products. Okay. So in this case, now the gamma A is a subgroup of the orthogonal group O B A. Okay, so the BA is a scalar product, right? So this gives us this orthogonal group of the non-degenerate, the scalar products BA, and of course it preserves the negative open set of A. Negative open sets of A. So what it exactly means? So OA minus, which is S X in VA, and this BAXX is less than 0. So in case this the BA has a signature P, 1, but then we have this hyperbolic space. The OA minus will be the hyperbolic space. So I will write it. So if the signature of A is P, Q, R, so the positive, negative, and 0 signatures, then as 0 eigenvalues, number of eigenvalues, then this VA is of signature PQ. Okay, and OBA will be naturally isomorphic to the OPQ. Then, so I think it's, I don't know, you remember at the first lecture, I introduced the cosine matrix from the Cox group, right? So the given Cox group WS, and then I mentioned the cosine matrix. So what was that? Do you remember? So GW, I denote by. So what was this cosine matrix? It was the -2 times the cosines pi over MST, right? So this was the cosine matrix. And then as you can see, the cosine matrix is a symmetric kata matrix comparable with the Cox group WS. Okay. So if this cosine matrix is irreducible and of negative type, then there is sigma CW, right? From the WS to the OBCW, which we call the Titz-Weinberg representation. Called the Titz and Weinberg representations of WS. Okay. So then, so at least, so you, previously, if you remember this WS, so the 7, 7, right? And then we have a corresponding cosine matrix. And then you can easily check, of course, this is irreducibles and also the negative type. So we have these representations from the WS to the OBCWs. Okay. In fact, these signatures will be the 5, 1. Okay. So this is a Titz-Weinberg representations. But as you remember, when I talk about the Cauchy function representations, then we need to know when the representation is convex co-compact, right? So now I think we have more general theorems for those, but at least the beginning versions is the combination of the Weinberg plus the de Groosen layers and the Hangulun's. At least the proof is in these papers. So what is that? So A is a irreducibles, symmetric, kata matrix of the signatures P1R, okay, and WA be a KAIST group comparable with A. And if for all T in S, the AT, so the notation AT is simply the restriction of A to T cross T. Okay? So the AT is not of 0 type, because the 0 type is related to the affine KAIST group. Then the subgroup gamma A, which is sigma A WA, right? Which is in the OBA. The OBA, of course, isomorphic to the OP1. And this is convex co-compact. Okay. So this is convex co-compact. In fact, if I use this cosine matrix of WS, then you can easily check that it's satisfying, of course, the irreducible, the symmetric kata matrix of signatures 5, 1, 0. And then you can also check here, there is no this the affine standard subgroup. The sub KAIST group, the special KAIST group, which is affine. Okay, so you can easily check for all T, the AT is not the 0 type, so it produced the convex co-compact representations. Okay. And this kind of the theorem is greatly generalized by the Jeff Denzinger, Francois Guerito, and Fanny Cassel, and me, and Ludovic Marquis in more general cases, but I think it might be takes too long to describe more. But at least I want to give the main idea to show this. Okay, so I drew these pictures. So at the hyperbolic space. Okay, and then if I draw.
One question, sorry, but is there some dimension condition here actually? So what is the dimension of this group X?
So you mean the dimension of the space or
of the space? So you have a
yeah, space. Okay, the dimension of the space is here, as you see that the R to the P, comma 1.
That's where it acts. Okay. So
Yeah.
itself is dimension P plus 1 plus R, right?
Yes, exactly. You're right. So yes, thank you very much for your questions. The Kata matrix has a dimension P plus 1 plus R. You're right. But if you remember the previous my descriptions, at the beginning we obtained this so this one. So this guy is a Cox simplex. So that's the dimension is the same dimension as the P plus 1 plus R. That's true. But then here we take the linear span of this guy. So then this space exactly the dimensions in this case the P plus 1. So then we obtain these representations. Here again, this VA is a dimensions P plus 1. So that's so then is it make sense or?
Yeah, so the BA always exists if you have a Kata matrix of this type, then the BA always exists. Yeah, I mean
yeah. So the BA itself exists always. I mean by definitions, BA. So the VA is a linear span of the BS tilde. So that's always exists. That's no problems. But the problems will happens when we want to have this Cox polytope. So here, okay, so here we have this this Cox polytope. But for example, if you take the A is a 0 type, but then okay, I think your question is very good. So maybe I think I should at least give the why something wrong when this assumption is not this assumption does not hold. Okay, so the point is, for example, let's imagine the Euclidean cases. So what I'm saying is that so I try to having a
so I guess one question is what is BS? I guess tilde here, and what is BS? I don't seem to understand.
Okay, so the BS will be simply the BS tilde. Because this is in the VA, right?
I mean what is BS to begin with? What is
BS? You mean the BS or BS tilde?
I mean the both, I guess.
Okay. So let's go back. Maybe I was too fast. Okay. So here the AP tilde is simply the dual basis of the RS. So if I write as a row vector, it's simply the 1, 0, 0, something like this, or 0, 1, 0, something like that. And then here, after that, we can easily take this BT tilde. So what will be the BT tilde? So it will be simply the column vectors of A, isn't it? Because A is, let's say, 2, 2, 2, minus 1, minus 1, minus 1, minus 1, minus 1. And then here, if I take A is something like this, in fact, this is a 0 type. The Cox simple, Cox Kata matrix, sorry. Then in this case, we should take 1, 0, 0. So I will write this linear functional as row vectors, and 0, 1, 0, 0, 0, 1. Okay, so this is a linear functionals. And then my bt tilde, so for example, the b1 tilde will be 2, minus 1, minus 1. And then the b2 tilde will be the minus 1, 2, minus 1. And b3 tilde will be the minus 1, minus 1, 2. Okay.
Okay, yeah, I see what you're doing. Yeah,
Yeah.
go. And then the
Okay.
just BS is what? And the just BS.
Oh, yeah. Okay. And then the V and just BS. So the BS, so this one is equal. Okay, maybe I should write. This is equal to B1. This one equal to B2. This one equal to B3.
But you restrict the subspace at the
Yeah, because the subspace VA exactly the span of
so
the B.
The space, yeah. Okay.
Yeah, VI tilde. So of course I just write the B1 is equal to B1 tilde, but here what I'm saying is that B1 is considered as a vector in VA.
Yeah, I see. Yeah, that's what you're doing. Yeah. Okay.
Oh yeah, okay. But I think thank you very much the question. And in fact, I want to take this particular example, but then I want to mention that there is something wrong because this is zero matrix. Sorry, the zero type. Sorry. So the zero type matrix makes some problems sometimes because so if you look at this VA, but then if you take the intersection with this guy, because the picture is something like this. So it has. So there are this. So how we can obtain? So this part is a cone. So this is the simplicial cone. Okay, and then these vectors v1, v2, v3. So v1 and v2 and v3. It will span the two-dimensional subspace, but the intersection is simply just one vertex. Just the origin, this one. Okay, so you cannot really construct cannot construct this projective polytope here. So this is we need this negative type. In fact, to put more precisely, A does not contain this. Okay. In fact, okay. The problem happens when A is reducible, and some components has a zero type. But I think for the convenience, I think because we always consider irreducible case, and then if you assume the negative type, then of course everything is fine. In fact, you can also consider the positive type too, but the positive type is not really interesting for me. So I assume that A is irreducible and of negative type. Then previous problem, something like this, never happens. Okay, so I think okay, so I think at least I want to mention so what is a rough idea or the main idea to show this convex co-compactness. So let's go back. So let's say this black one is my PA. Okay, so everything, the black one. But then to get this convex co-compactness, what we wanted to do, so this every face. So in this case, H. So this will be, so okay, maybe I think I write here. So this one will be related to the corner of alpha S, right? And then there will be these points, the vertex, which is BS. Okay. So the sum error here, the sum error here. So of course, if I take this part, and then it will be the everything, right? But we want to find some convex closed set preserved by this reflection group, right? So how we can do? It's quite simple ideas, but it's important. So this is this red dot corresponding to the reflection vectors, and then take the convex whole of these reflection vectors. So okay, and then take the intersection with PA. So understand? So this, it will be the PA intersection with the PA star. The PA star is exactly the convex hole. So this PA star is a convex hole of the reflection vectors. Okay. But then, if you take the gamma A orbit of these intersections, then this will be the surprisingly convex, and also the closed set in this the HD. So PA intersecting with the PA star is in OA minus. So in our case, will be the HD. Okay, so I stop here for the second lectures. And is there some questions?